Hello everyone, welcome to my class. In today's class, I am going to cover limits and continuity of function of two variables. So let me start the class right away. So our goal in this section is for the function of two variables f and a given point ab in the domain of f, we wish to find out whether the following limit exists or not. The limit of f as xy approaches to ab equals to L. If this exists, then we say the L is a limit, and if the limiting value of functions at AB equals to function value at AB, that means function is continuous. Next, let me give you the definition of limit. We say that the limit of f as xy approaches to AB is L, and we mathematically write as limit of fxy as xy approaches to AB is L if and only if f approaches the limit L as the point xy approaches to the point AB along any path within the domain of f. So in calculus 1 we studied the limit. There we approach a point in two directions, either from the right or from the left. But here we are approaching to the point along any path inside the domain of the functions. Now in limit definition in terms of epsilon and delta language, so for every epsilon positive there exists a positive delta, such that whenever the distance between x, y and AB is less than delta, then the distance between fx and L is less than epsilon, which is easier to understand from this diagram below. So we pick up point AB in the domain of our functions, and we are approaching to AB to either direction, means we are squeezing this delta ball, going closer and closer to AB. Then our function value here, we are inside these intervals L minus epsilon to L plus epsilon, and we are going closer and closer to L. Great. So let's move on. So next definitions. Two path test for the limit does not exist. The limit of f as xy approaches to AB does not exist if f has a different limit as the point approaches to the fixed point AB along any two different paths. So to show the limit does exist, we need to find out any two different paths where limits are different. Squeeze theorem. Suppose given functions f, then we want to find two other functions g and h, such that we have this inequality: g function is less than or equals to f function less than or equals to h function, and as xy approaches to AB, g function has limit L, h function has limit L. Then the conclusion of this squeeze theorem is the middle function f also converges or has a limit same L. Quick remark: polar technique. To find the limit as xy approaches to origin, use x equals to r cosine theta, y equals to r sine theta. Then we have x square plus y square, or it should be y square equals to r square, and as xy approaches to 0, then limit will be r approaches to 0 from positive side. Great. Quick note: to find the limit as xy approaches to 0 along any straight lines through origin except the vertical line, use y equals to mx, where m is slope. Next definitions about continuity. A function of two variables is continuous at given point AB if and only if the limiting value equals to the function value at that point. Intuitively, this means that the surface has no hole, no tear at that point P. Quick example: the temperature functions, the T depends on longitude, latitude, altitude, or maybe time, is continuous. A polynomial in two variables is continuous. Awesome. So now with these definitions, now let's do some example. Example 1, evaluate the limit of x square y cubed minus 4y square plus 9 as xy tends to 1, 2. So here x approaches to 1, y approaches to 2. Since this is a polynomial, it's a continuous, we can plug the value directly. So put x equals to 1, y equals to 2 and simplify, it gives us 1. So the limit of these functions is 1 as xy approaches to 1, 2. I hope this makes sense to you all. Now let's move on to example 2. Find the limit. Our function is under the radical x squared minus y cubed, and as xy approaches to 1, 2. So put x equals to 1, y equals to 2, but this gives us another radical minus 7. It's not a real number. That means limit doesn't exist as a real number. So the limit does not exist. Example 3, evaluate the limit of this fraction functions x square y over x square plus y square as xy approaches to origin, if exist. So solutions. So here the domain is everything in R2 except origin, and we compute the limit along various lines through origin. First, along x-axis, put y equals to 0. On this function, put y equals to 0. So numerator is 0 over x square. 0 over x square is 0. So the limit of these functions means 0 function from calculus 1. The limit of the constant is constant. So limit is 0. Along y-axis, put x equals to 0. Again, our function is 0. So the limit is 0. Along any non-vertical lines through origin, that is along y equals to mx, m is slope, put y equals to mx, so here x square, y equals to mx, so mx cubed over x square plus m square x square, so this should be m square here. Then take x square out and cancel, so it gives us mx over 1 plus m square. So then our limit, when you take x goes to 0, that means this mx over 1 plus m, by the 1 plus m is a constant, so x goes to 0 means this goes to 0. That means we have the limit of this function along the line y equals to mx. So now we have 0, 0, 0 limit so far. Let's try along the parabola y equals to x square. Put x equals to, put y equals to x square. So then here x square times x square is x to the 4 on my numerator, and on the denominator x square plus x square is x to the power 4 there. So simplify. Now take the limit as x goes to 0. Again numerator goes to 0. That means limit is 0. So along every path we found limit is 0. Consequently the limit exists of these functions, which is 0. I hope this makes sense to you all. So now let's move on. Example 4. Let's revisit example 3 again using squeeze theorem. Evaluate the limit of x square y over x square plus y square as xy approaches to origin. So let's try to find the bounds of these functions, means the functions smaller than these functions and the functions bigger than these functions. So let's start with this known fact. Since x square is positive and y square is positive, so x square over x square plus y square is less than or equals to 1 and is greater than or equals to 0. So this part is 2. Then what I need? Now I need y there in my numerator. So let's multiply by absolute y, means the positive y. Still the inequality is true, and as y goes to 0, that means if y goes to 0, then obviously the absolute value of y also goes to 0. Then by squeeze theorem, here this goes to 0 as y goes to 0. This goes to 0 as y goes to 0 because left side is 0, so even I don't need to worry about this absolute y on my left side. So as y goes to 0, this functions goes to 0, this functions goes to 0. Then by squeeze theorem, the middle functions also goes to 0. So that means we have the absolute value here, by the way. All numbers are positive and y is positive. That means this goes to 0, and we know absolute convergence implies convergent. Then the function without the absolute value also converges to 0. Hence, the limit of these functions x square y over x square plus y square as xy approaches to 0, 0 is 0. I hope this idea makes sense to you all. Now, a quick aside. So clearly these functions, if I define this function piecewise, f equals to x square y over x square plus y square for xy not equals to 0, 0, and f equals to 0 for xy equals 0, 0 is continuous at the origin. Great. Let's move on. This is example 5, a polar technique. Evaluate the limit of these functions. Function is x square plus y square times natural log x square plus y square as xy goes to 0, 0. So solutions. So in polar technique, we put x equals to r cosine theta, y equals to r sine theta, then square and add both sides. This should be y here. Then r square equals to x square plus y square, and as xy goes to 0, 0, r goes to 0 from right side. Thus, our limit reduces to in polar form. Limit r goes to 0 plus x square plus y square is r square times natural log of r square. Then put r equals to 0 is 0. Natural log 0 is infinite. That means this is an indeterminate form. Now I need to apply L'Hopital's. So to apply the L'Hopital's, let's write this function in a fraction form. So let's bring r square in the denominator by writing its reciprocal. So I can rewrite this function this way. Limit r goes to 0 plus ln r square over 1 over r square. Then put r equals to 0. This is infinity over infinity. So this is indeterminate form. Let's apply the L'Hopital's. So take the derivative of ln r square, which is 2r over r square. Take the derivative of 1 over r square in the denominator, which is minus 2 over r cubed. Simplify. It gives us negative r square, and take the limit. This goes to 0. Hence, the limit of this corresponding functions in terms of x and y also 0. I hope it makes sense to you all. Now let's move on. Example 6. Evaluate the following limit. Limit xy tends to 0, 0 of xy square over x square plus y to the power 4. Again here, domain is of this function is everything but not origin. Now let's compute the limit along these lines. Along x-axis, put y equals to 0. So function is 0. That means limit is 0. Along y-axis, put x equals to 0. Function is 0. Then limit is also 0. Along the line y equals to x, put y equals to x. Simplify. Then as x goes to 0, this function also goes to 0. Along non-vertical lines, y equals to mx, put y equals to mx here. Maybe that's better. Then simplify. Take x goes to 0. Again, the limit goes to 0. However, along the parabola x equals to y square, put x equals to y square. Simplify, which gives 1/2 constant functions. Then the limit is also 1/2. So then 1/2 not equals to 0. So that means the limit of these functions does not exist. Great. So another example 7, limit of sine of x squared plus y squared over x squared plus y squared as xy goes to 0, 0 is 1. Please work out and get this limit and make sure you got this. So with this homework, we finish these sections. So thank you.